So previously we solved on finding the optimal solution type problem using the graphical method for a maximization function. Now we're going to do the same for a minimization function, and you'll find it's quite similar. So let's get started. This is question 3.2. In question 3.2, they give us the objective function, which is a minimization function, equals z equals 4x1 plus x2. So once again, we're going to have to, let's give this function an index of 1. So once again, we're going to have to optimize this function subject to a couple of constraint functions. So here are our constraint functions. The first constraint function, we're going to give it index 2, is going to be x1 plus 3x2 equals 9. The second constraint function is going to be, we're going to give it index of 3, is going to be x1 plus x2 smaller or equal to 5. And as usual with these linear programming problems, we have non-negativity constraints, which are simply x1 bigger or equal to 0 and x2 bigger or equal to 0, so as to not get negative values for our variables. So our first step is going to be to find points on the constraint functions and then use those points to graph or graphically represent these constraint functions. So let's do that for the first one. Constraint function indexed 2. If we replace the variables x1 and x2 and solve for the other variable, we can find 2 points. The first point will be 0 and 3. Right? Because if x1 equals 0, then x2 is going to be 9 over 3, which equals 3. And the second point, if we replace x2 by 0, we're going to get that x1 equals 9. And those are our 2 points for our constraint function indexed 2. Now we can do the same for constraint function indexed 3. It's the identical process. You replace x1 to find x2 and vice versa. We're going to once again use 0 because that's the easiest. So here we have x2 equals 5. And because it's a very simple function, x1 is going to be 5 and x2 is going to be 0. Now we can, x1 bigger or equal to 0 and x2 bigger or equal to 0 is, these are just lines along the axes. So let's go ahead and graph this. This is going to be our x1 axis. This is going to be our x2 axis. And let's put some numbers. Start over here. 1, 2, 3, 4, 5. So let's start by graphing out our constraint function, the first of our constraint functions with coordinates 0, 3 and 9, 0. So coordinate 0, 3 is going to be here. Coordinate 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is going to be here. So this is constraint function indexed 2. And if we do the other constraint function graphical representation, it's going to be starting at coordinates 0, 5, 4, 5, and 5, 1, 2, 3, 4, 5. This is our constraint function indexed 3. We also need to graphically represent the objective function z equals 4x1 plus x2. And to do so, we will equate it to an arbitrary value, let's say 5, and then plug in zeros for x1 and x2 to get some coordinates and be able to find the corresponding line on the graph. So let's go ahead and do that. So if we have 5 equals 4x1 plus x2, and then we plug in 0 for x1 and then once again 0 for x2 and solve for the other variable, x1 and x2, we'll find 2 coordinate points. So let's say x1 equals 0. That means x2 is going to equal 5. That's our first coordinate point. And if we have x2 equals 0, x1 is going to equal 5 over 4. So now that we have these points, we can plug them or like draw them onto the graph. So for 0 and 5, it's going to be over here. And 5 over 4 is going to be just over 1, be somewhere over here. And our objective function is indexed at 1. Now, typically, we would plug in coordinates on either side of each of these lines to find out where the feasible region of solutions lies. And this would work in most cases, for example, for constraint function 3 and for the non-negativity constraints, x1 and x2. We'll just go ahead and draw them in really quick with pink. Here we are. This is x2 bigger or equal to 0 and x1 bigger or equal to 0. However, here we also have an equality constraint. So as mentioned previously, because our feasible region is here, here is a line that lies on the graphical line of constraint function x1 plus 3x2 equals 9. We now have to delimitate that using the other constraint functions, meaning the non-negativity constraints, as well as our second constraint function x1 plus x2 smaller or equal to 5. We will do the same thing as what we did with the optimization problem, where we propagate the optimization objective function through our graph. And for a minimization function, our optimal solution is going to be one of the points at the extremities of the feasible solution. Now, because our feasible solution here is a line, which is somewhere along this line, there are only 2 points that can be considered as our optimal solution, here and here. So we have to find these points. For this point, it's quite easy. We just plug in coordinates 0 and 3 for x1 and x2 into our first constraint function indexed at 2. So it's going to be 0 plus 3 times 3 equals 9. Here we can check and verify that our constraint function is satisfied. So 0 plus 3 times 3 in fact equals 9. So you could see that this point is definitely part of our feasible solutions. So we can go ahead and write the point over here as 0 and 3. Now, for the other point, this one, we have to equate our two constraint functions to each other and solve for this point. So here we can begin by solving for, let's say, x1 in our second constraint function. So we'll do it over here. x1 is gonna equal 5 minus x2. Now we can go ahead and plug this value for x1 into our first constraint function. So it's going to be 5 minus x2, right? That equals x1 plus 3x2 equals 9. If we solve for x2 here, we will find that x2 equals 2. Then if we plug this x2 equals to 2 into our first version of the second constraint function, x1 equals 5 minus x2, we're going to get that x1 equals 3. So that's going to be our point here. And as you can see, granted my drawing is not perfect, it lines up roughly with 3 and 2. Now, our optimal solution for a minimization function is when using the graphical method and we propagate the line of the objective function through our graph and hit all of these extremities. In this case, there are only two extremities because, as I mentioned previously, the feasible solution area is in fact a line, is going to be the last point hit as you propagate the line from the upper right corner, the first quadrant of the Cartesian graph, towards the origin. Of course, even if we did have a feasible region, we could not use the origin, 0.00, as an optimal solution, as this would just give us 0 for both variable values, and that would defeat the purpose of the optimization problem. Here, the last point hit is going to be 0, 3. So our optimal solution, using the graphical method, is going to be 0 and 3. So here we found the coordinates of the optimal solution, 0 and 3. That was 3.2, and the part of the question was 3.2.1. And there's our solution. Now for 3.2.2, like in the maximization problem we did previously, it asks us to find the value of the objective function, the optimal value for the objective function. So the way we do that, 3.2.2, is by plugging the optimal solution coordinate, 0, 3, into the objective function. So let's go ahead and do that. So we're going to have z is going to equal 4 times 0 plus 3. Here we clearly see that 4 times 0 plus 3 is going to give us the value of 3 for 0. Now, in order to check our answers and ensure this is correct, we can also plug in the other value that's within the feasible region, which here is the line that's previously mentioned, and this value is 3 and 2. Let's go ahead and do that so we can check our solution. So 4 times 3 plus 2. 4 times 3 is 12, plus 2, 14. Now, since this is a minimization problem, let's say hypothetically you're trying to minimize costs. You would want the smallest value as your optimal solution, right? Because you're trying to minimize something. So here our solution, or our optimal value to our objective function, is 3. Question 3.2.3 asks, it's a little bit more of a conceptual question, and it asks us to identify all feasible solutions of this linear programming problem. You may use a sentence or a math equation with reference to the graph you have drawn in solving this part. The reason they would ask this is because here it can be explained with just a line. If it was an entire region, there would be infinite amount of feasible solutions. Even here there are infinite amounts, but they're just trying to explain, to get you to explain how the feasible region here is a line. So we can write this solution as so. 3.2.3, and we can write this as all values along constraint function along constraint function, which was our first constraint function. I've erased it here, but we have it here. Our first constraint function, our equality function, was x1 plus 3x2 equals 9. So all of the values for x1 and x2 along this line between this point and this point are all feasible solutions to our optimization problem here. So we can even write it as for x1 belonging to 0 and 3, right? Because it x1 ranges from 0 until 3. And for x2 belonging to 2 and 3. Because x2 can only range between 2 and 3. Thank you. I'll see you in the next video.